Good day, everyone. Today, I will explain the fundamental concepts behind the pressure, depth, and Pascal's law in fluids, its derivation, and its application in analyzing fluid behavior. Let's take a closer look at the provided visual presentation. Now, we have pressure, a hydrostatic pressure equation in fluid mechanics. It describes the pressure at a given depth in a fluid due to the weight of the fluid above it. In a static fluid, the pressure at the given depth is given by the formula. This equation shows that the pressure increases with the depth due to the weight of the fluid above. It is crucial in engineering, oceanography, and hydrodynamics for understanding the fluid behavior in various applications. Before we proceed to the direct formula, we need to know the terminology of the formula. The formula we are discussing relates to the pressure exerted by a fluid at a given depth. Let me define the key terms. We have P sub 2 equivalent to P sub 0 represent the pressure at the surface of the fluid, which is typically called atmospheric pressure. Second, we have P sub 1 equivalent to P indicates the pressure at the level within the fluid. Third, we have H equivalent to Y sub 2 minus to Y sub 1 refers to the depth from the surface to point 1 where Y sub 2 and Y sub 1 are vertically positions. The second to the last, we have ρ, denotes the density of the fluid. Lastly, we have g, represents the gravitational acceleration, typically 9.81 meter per second squared. Now, we have a illustration of the fluid diagram. The diagram provided visually represents the system. First, we have point 2 at the fluid surface shows the pressure as P sub 2 equivalent to P sub 0 that automatically called a atmospheric pressure. Second, we have point 1 at a depth of height shows the pressure as P sub 1 equivalent to pressure. The difference in height between these 2 points is represented by y sub 2 subtract to y sub 1 equivalent to h or height. The fluid has a density and gravitational force acts downward. Now we have derivation of the formula. Let's break down the derivation. As you can see, we have initial formula is P sub naught subtract pressure equivalent to negative density times gravity open parenthesis y sub 2 subtract y sub 1 close parenthesis. This equation arises from the relationship between fluid pressure and gravitational force. Second, we simplify gives P sub naught subtract pressure equivalent to negative density times gravity times height since the close parenthesis y sub 2 subtract y sub 1 close parenthesis is equal to height or h. Lastly, we rearranging the equation yields the final form of pressure equivalent to P sub naught plus density times gravity times height. This formula illustrates that the pressure at the given depth is the sum of the surface pressure and the pressure due to the weight of the fluid column above it. Now, if you know how to derive the formula of pressure, then you need to practice your skills to solve a problem set. We have problem set 1 and problem set 2, and we need to check after the event of DNSE.
Now, let's talk about depth. Depth measures of how far down something extends, like a depth of an ocean or a depth of a pool. So, basically, we understood depth as kalalumun. So bata pa lang ta, nakabalo na ta kung unsay depth, right? So mo na siya ang kalalumon. But I have a question, class. How depth is related to pressure? Ang inyo lang yung hinumduman, class, is that magkalalom gani ang water, magkadako po ang iyang pressure. Ganuman, it is because of the weight of the water. So, imagine, class, that the water at the top pushes the water nga naa sa bottom, leading that the pressure at the bottom increases. So, I have here an illustration showing the pressure. So, if we have pressure in P sub A going to P sub B in a horizontal manner, the pressure in P sub A to P sub B is just the same. That's why P sub A is equal to P sub B. Similar gihapon siya diri sa ubos nato, similar to our P sub C to P sub D, the pressure is just the same. If we move the P sub C going to P sub D in a horizontal manner. But we assume nga ang makuha nato diri sa P sub C to P sub D na pressure is different from the P sub A to P sub B na pressure. Because if mao ni atong pressure 1 and mao po ni atong pressure 2, let's keep in mind that pressure 2 is greater than pressure 1. Why is that so? It is because of the weight force that influenced by the density and gravity. So one example in a class is that kanang cellophane or anything cellophane. Naba mo cellophane nga ice water, kanang sa ice water, sudlanin niyo na og tubig, punon niyo og tubig, then mangita mo og object na something pointed like lapis. If imuha nang tuslukon ang cellophane nga nay water dara sa bottom part, unsay manita ba sa tubig, di ba mulugsot di kayo, kusog kayo ang flow sa water. Compare if imuha siyang tuslukon sa babaw na part, unsay mahitabo sa tubig, so dili kayo mo dagayday or dili kayo mo flow or dili kusog ang pag-flow sa water. So from that example, we can conclude now that the pressure at the bottom is greater than the pressure at the top. So if mo tanong mo, class, nga kano saan man mag-change ang pressure, ma'am? Kano saan man siya mag-vary? So mag-vary lang ang pressure depending sa height or elevation sulod sa fluid. Munang naata diri na-express na something like equation. So naatay differential 1 raised to the power of 2 dp is equal to negative rho. So mo ni atong density times gravity differential 1 raised to the power of 2 dy. So ang kaning atong dp mao ni ang atong pressure, and then ang dy nato mao ni ang atong height or elevation. Kaning negative rho mao ni atong density times gravity, constant lang ni siya. So ang inyong hinumduman, class, nga mag-vary lang ang pressure depending sa height or elevation. Moro yun na siya, class, moro yun na inyong hinumduman nga mag-change lang ang pressure kung ma-change po ang iyang elevation.
So let's discuss the forces acting in a fluid, both horizontal and vertical forces. So if a fluid is in hydrostatic equilibrium, it means that the forces acting on it are balanced and the net force is zero, and this balance ensures that the fluid remains stable and doesn't accelerate or it does not move on its own. So proceeding to the left side of the diagram, as we can see here, the df sub A is equals to the df sub B. So in the diagram, the forces on the left side and the forces on the right side are equal in magnitude, and when the fluid is in hydrostatic equilibrium, so these forces are balanced and they cancel out each other out, maintaining stability. So the df sub A, what is the magnitude in the df sub A, is always exact equal or the same amount to the df sub B. So however, if the fluid is in motion, these forces will be no longer equal because one may experience greater force than the other, or leading to the fluid movement. So it's either the df sub A is greater than the df sub B. So in vertical forces, where the right side of the diagram, as we can see here, the dF sub 1 is equal to the dF sub 2. So it is similar in the vertical, in horizontal direction. The forces also balance out, and when the fluid is in hydrostatic equilibrium, it also resulting in zero net force. So the pressure gradient force is balanced by the gravitational force, or it counteracting the gravitational force that pulls downward, and also this balance prevents the fluid from accelerating. So the pressure gradient compensates for the weight of the fluid column above a certain point, or as depth increase, the pressure increase due to the weight of the fluid column above. So this means that the deeper you go in a fluid, the greater the pressure exerted at that point. So next is the Pascal law. So Pascal law is the pressure applied to an enclosed fluid is transmitted and diminished to every portion of the fluid in the walls of the containing vessel. So in Pascal law, in layman's term, is think of a sealed plastic bag with filled of water. So if you squeeze the one part of the bag, you'll notice that the water pushes against all sides with equal force. So this happens because liquid like water are nearly incompressible, so any pressure applied to one area gets transmitted equally throughout the entire bag. So no matter where you squeeze, and the pressure spread in all direction. This is simple way to observe the Pascal law, which states that when pressure is applied to a confined fluid, it is distributed evenly throughout the fluid. So you can squeeze the one side and feel how the pressure transfers in the bag. So the walls of the bag is equal force because of the force that you apply. So this is how the fluids behave in a closed container, and when you apply pressure at one point, it spreads equally in all direction without losing strength. So this principle is why hydraulic systems like car brakes and hydraulic lifts work efficiently. So this is the formula of the Pascal law formula, which is the F is the force applied, the P is the pressure transmitted, and the A is the cross-sectional area. So as you can see in the triangle formula, where the F, if the F is missing, you have to multiply the pressure and the area or the cross-sectional area. Whereas if the area or the cross-sectional area is missing, you have to divide the forces and the pressure. It also, in the pressure, you have to divide the forces and the pressure. So sample problem for the Pascal law. A pressure of 2000 Pascal, or the Newton per square meter, is transmitted throughout a liquid column due to a force being applied on a piston. So if the piston has an area of 0.1 square meter, what force is applied? So the missing, or the required of the problem is the force. So we have the pressure and we have the area, where the pressure is the 2000 Pascal, or the 2000 Newton per square meter, and we have the area of 0.1 square meter. So the formula here is, since the force is missing, or the required, we have to multiply the pressure and the area, where the pressure is 2000 Pascal times multiply by 0.2 square meter, where the answer is 200 Newton, because the square meter is cancelled out by the both of the given, where the Newton is also the force, so that the answer is the 200 Newton.
Now let us proceed to the application of Pascal's law. According to the Pascal's law, pressure applied to an enclosed fluid is transmitted and diminished to every portion of the fluid in the walls of the containing vessel. This illustration shows how Pascal's principle is applied in the given hydraulic system to lift a car. In this system, a small force, which is the F1, is applied to a smaller area, A1, generating pressure, which is the P1 equals F1 over A1. This pressure is transmitted equally through the incompressible fluid to a larger area, A2.
generating a larger force, which is the F2 equals P2 times A2. Since the pressure is equal throughout, P1 equals P2, therefore, the output force F2 is 10 times greater than the input force F1. This allows a small force to lift a heavy object like a car. In simple explanation, the hydraulic system uses Pascal's principle to amplify the input force. A smaller force applied to a smaller area creates pressure that is transmitted equally throughout the confined fluid. This pressure acts on a larger area, resulting in a proportionally larger output force capable of lifting the car. The output force is 10 times the input force. This principle is applied in hydraulic lifts. Hydraulic lifts use Pascal's law to raise heavy objects like cars in garage or heavy machinery in the factories. A small pump creates pressure in the hydraulic fluid, which is then used to lift the heavy object. Hydraulic elevators, which are commonly used in low-rise building, also use Pascal's law to lift the elevator car. A hydraulic piston, powered by pressurized fluid, moves the elevator car up and down. Lastly is the hydraulic brakes. When you press the brake pedal in a car, you're applying force to a small piston in the master cylinder. This force creates pressure in the brake fluid, which is transmitted equally to pistons at each wheel. The larger surface area of the pistons at the wheels amplifies the force, effectively stopping the car. As for gases, the assumption that density is uniform is realistic only over short vertical distances. For example, the standard height of the common living room from floor to ceiling is 3 meters. The uniform density can be applied, which means that calculating the density is the same throughout the area. However, it is not applicable in greater heights like Mount Everest. This means that the calculation of density is different in the peak and different in the base. So that's all for our report. I hope that you've learned something. Thank you.